Hello my YouTube friends, today we're looking at Norton's equivalent circuits. Previously we looked at Thevenin's circuit, which is not very different from the Norton's theorem. So let's see what this theory is all about. So first of all, we have to understand the definition of what Norton's theorem states. And this is any circuit containing independent or dependent sources and resistances that can be replaced or reduced to an equivalent circuit that will only consist of just a current source and a resistor parallel to each other, like so. And if you remember previously when we looked at the Thevenin's theorem, we had a voltage source in series with a resistor. So this is the difference between these two theorems. But in terms of calculations, they are very, very similar to one another. Now, if in the circuit there's no voltage or current sources, then the Norton equivalent circuit will only consist of a resistor like so, and this resistor is the same as the Norton's resistor. So you can call it a Thevenin resistance or you can call it a Norton's resistance, but it's one and the same. The same procedure that we use to calculate the Thevenin's resistance is the same procedure that we use to find the Norton's resistance, and that is how it is done. Now, if we come to the step-by-step analysis, so what you do first of all is to find to replace the load resistor by a short circuit. So a short circuit is simply a wire connection that replaces the connection where the load resistor is between those terminals. So if you have terminal A and B and there's a load resistor in between there, you replace it by simply a wire that causes or is what we call a short circuit. And then further from that, we compute the short circuit current ISC, which we call the Norton's current, and this is, when we find it, is what we call the Norton's current. And you can use any preferred method: mesh, nodal, voltage divider, superposition, any method that suits you to find this value of the short circuit current. And then afterwards you determine the Norton resistance, which we are calling the Rn, which, as I mentioned, is equivalent to or the same as the Thevenin's resistance. And we have to find this by zeroing the sources. So we zero the current sources by replacing them with open circuits, and we zero the voltage sources by replacing them with short circuits. And from there, you can now create or draw your equivalent circuit, which will appear like I had shown earlier. So it will appear with a current source in parallel with a resistor, and then you have the load terminals there like so. So AB. So this is where the load resistor was. So this is going to be your R Newton, and this is going to be your I Newton, and this is what we are calling the Norton's equivalent circuit. And you find this to be equal to the short circuit current, ISC, the short circuit current. Okay, so in place where you have, like I mentioned, if you have the load resistor, RL, and you replace it by a short circuit, if you come here, you replace this by a short circuit, you notice that all the current flowing from the current source will flow through the short circuit current Why? Because current always prefers a path of less resistance. So in the short circuit, the resistance is very minimal, it's almost zero. And then in the resistor here, the resistance is very high, so the current is going to avoid the path with high resistance and follow a path of minimal resistance, in this case the short circuit current. That is why the Norton's current is equal to the short circuit current. I hope that is clear. So from there we can look at one example, and this example we've been asked to determine the Norton current and the Norton equivalent for the circuit shown. So we've got a load resistor which is here 10 ohms. We've got a resistor there, 2 ohms resistor, 2 is 3 ohms resistor, 1 is 6 ohms, and we've got a current source of value 2 amps, and then we've got a voltage source which has a value of 6 volts. So now let's go on and see how to solve this circuit. So when it comes to solving this circuit, first of all we want to look at how we can get some of the values sorted out. For instance, the equivalent resistance as the first step. So I'm choosing to use the equivalent resistance first. We solve that, and then next we go on to look at how we solve the Norton current. So in this case, the first procedure is we zero the sources. We zero the current source by replacing it by an open circuit, which is here. So we've replaced the current source with an open circuit, and then we replace the voltage source by a short circuit. So we replace the voltage source by a short circuit. The load resistor has been removed, so you've got A, B, like so. And what remains now is that our equivalent resistance, or our Norton resistance, is going to be equal to, so we're looking at the circuit from the terminals to find our Norton's resistance, what we call the resistance at the terminals. And then we calculate it coming from far away from the terminals. So we're starting from R1 going towards the terminals. And in this case, R1 and R2 are parallel to each other. And therefore, and then when we find the combination of the resistances between R1 and R2 parallel, then the equivalent resistance that we find here is going to be in series with the resistor 3, giving us the total resistance in that way. And if you remember, R1 is 6. To find the parallel circuits, parallel resistances is going to be 6 times 3, and this will be divided by 6 plus 3. This adds to R3, which is a 2 ohm resistor, and this should be able to give us, you've got 18 divided by 9, which is basically 2 plus 2 gives us 4 ohms. And therefore, between the terminals A and B, the equivalent resistance that we have found is a 4 ohm resistor, which is indicated or shown like so. So this is the equivalent resistance. Now we look at how we find the Norton current, and then we make the equivalent circuit. Now let's continue to look at solving the Norton current. So I've redrawn the circuit here, and as you can see, we've got the terminals. We've removed the load resistor and replaced it by a short circuit, which is the short circuit, the connection I'm showing here. And then we have the voltage source, the current source, as the circuit is. So in my case, I want to use node voltage method and see what results we obtain. So I'm gonna ground the lower part of the circuit, and if I come to node voltage analysis, then I'm going to identify and label my voltage, my node here as node 1, which I assign V1, and node 2 I assign V2. This is node 3, which is at 0 potential. And then, as you can see, we have a voltage source that is between two non-reference nodes. So we consider this as a supernode. Okay. So knowing that this is a supernode, then we're going to have several equations. Here at resistor 1, we've got the current flowing into ground, and we've got the current flowing also there into ground. We've got the current source entering that node, that supernode. So first equations are going to be at supernode. So at supernode, what we have is that we have V2 minus V1 should be able to give us Vs. Or we can say V2 minus V1 should be able to give us 6 volts. That's our first equation. And then the second equation is, this equation is what we call inside the supernode. So this is inside, and then at the supernode, what we have is now what is entering this circle and what is leaving that circle. Remember, we're applying KCL. Sum of currents entering a node must be equal to the sum of currents leaving that same node. So when we look at this here, we are saying we've got our IS, which is this source entering, and the rest are leaving. So IS must be equal to the current here, which is going to be V1 over resistance over R1. This should add to the current here, which should be V2 divided by R2, plus the source, the short circuit current here, which is going to be V2 over the resistance there, which is 2 ohms, and we've got R3 there. So when we replace in the values here, we get to have we've got 2 amps there. 2 amps should be able to give us V1. So what is common here? What we have here is simply we only have one V1 here. So it's V1. We've got 1 over R1 is 6, and then we have V2. We have 1 over R2. R2 is 3. 1 over 3 plus 1 over, which is R3, 1 over 2, giving us the solution like so. So if you look at this, the common here is 6. So you've got 6 here. You've got 2 plus 3, which is 5 over 6, basically. So we could eliminate this fraction. We multiply everything by 6, which gives us 12 here. So 12 is going to be equal to this remains simply V1, and so this 6 and 6 cancels, and then here we remain with plus 5 V2. And then we've got 2 equations that we are going to solve now simultaneously. So you've got the equation the equation 12 equal to V1 plus 5 V2, and the equation V2 minus V1 equal to 6. So I'm going to transfer these 2 equations onto the next page. So we've got equation 1 is V2 minus V1 equal to 6, and then equation 2 is 12 equal to V1 plus 5 V2. So we can replace V2 V2 in this equation and get our solution. So when we do that, we can find first we can find the solution for V1. and then we get to find the solution for V2. Okay, we get to find the solution for V2. So when you manipulate this and solve, you can regroup them if you want. So you can say, for instance, you can say V2 equal to 6 plus V1, and then you replace that in here. Okay, so what you have is now 12 equal to V1 plus V2, this is 5, V2 is 6 plus V1. And when you get to solve that, you have 12 equal to, you've got 30 here, and then you've got 5V1, so which gives you 6V1 plus 30, from which you can now find V1. V1 should be able to give you, you've got 12 minus 30, then divide by 6, so you've got 18 basically, minus 18 divided by 6, which gives you minus 3 volts. And then you go on to using this. Now we have V2, which can be found now from the equation above. You can say V2 equal to the voltage source, which was 6 plus V1. So the voltage source was 6, and V1 we found it to be minus 3, and therefore V2 gives you 3 volts. And if you remember, when we looked at the circuit, we're saying our source, our short circuit current, the short circuit current should be able to be obtained from, if you look at this circuit, so the short circuit current should be obtained from the value V2 divided by the resistor 3, which is 2 ohms. So when we come to our solution for the short circuit current, then the short circuit current is V2 over R3, which is basically V2 is 3 divided by R3, which is 2, and this should be able to give us 1.5 amps as our short circuit current. Now, if we find the short circuit current, we are saying the Norton's current is therefore equal to the short circuit current, which is simply 1.5 amps. And we could go ahead and say the final circuit now appears as follows. We've got the Norton's current parallel to the voltage source, the resistor, and then we've got the terminals where we can connect the load resistor here. So AB, we've got, you remember we calculated the Norton's resistance to be equal to 4 ohms, and then the Norton's current, which is equal to 1.5 amps. And this is our Norton equivalent circuit. So this is how you find the solution. If you've been asked for further calculations, you could add the load resistor and find now the current flowing through the load resistor, and so on, using this equivalent circuit. That's our Norton equivalent circuit. Okay, and this question could be solved very easily if you apply mesh analysis. You can use superposition method, and what I would suggest is, in the comment section below, I want you to at least solve and put up your solutions using mesh, and others can use superposition, and see if we arrive to the same solution. So I'm glad that you've learned to we've looked at how we solve these questions, and eventually we found that the solution here is the equivalent circuit is basically a current source parallel to a resistor that is of value. So then we can connect the load resistor here, and what we have found is this is 4 ohms, this is 1.5 amps, and then this is our load resistor, and this is the equivalent circuit from this large circuit to that equivalent Norton equivalent circuit. Basically, that is how you handle these circuits, and they're pretty easy. It's the same as Thevenin's theorem. All you have to do is apply the knowledge that you've collected prior to this, which is the analysis methods, mesh, nodal analysis methods, superpositions, and so on. Okay, and that is how we get to this answer. So we've looked at everything. From this scenario, we've sorted it out until we've found our equivalent circuit. Thank you for watching. Like I said, I want others to solve the same question using mesh, and another group to solve using superposition. Mesh and superposition, and let's see if we arrive to the same answers. Thank you for watching. Subscribe to my channel. Stay safe. Good day.